In this chapter, we're going to look in this video, we're going to look at some chapter 7 problems. Chapter 7 problems. And we'll take a look at 7-11. So probably on this one, as always, it's good to start with a free body diagram. And maybe make something like this. And so let's say we have a force FBD. And at C, we have some reactions. Say CX, CY. And let me take another look at that picture there. And we have C, FBT, and then B is, yeah, basically right here. And then you have E over here. And then you have a certain load over here. On mine, it's like 2 kilograms. Of course, always remember that, remember to convert that to newtons. And so you want to find the force in FBD. So the best thing would be to sum the moments about C and set that equal to 0. And of course, this, remembering over here, this is 75 degrees. So we want to start with that. And then once you've done that, that will give you, it gives FBD. So you'll get FBD from that if you sum the moments about C. And then you can look at your little element here. Let's see, they want to know the internal loading on point E. So you can sort of think of like cutting E along E right here. And then you'll have like maybe VE, have some ME, and some normal force here. And so what you could do is then look at everything. Like, for example, we can pick everything to the right of VE. Remember, when you're doing these internal loadings, you can either pick like everything to the left or pick everything to the right to work with. So we'll pick everything to the right. And then what you could do, so VE, so what you could do this, you could say like VE is going to be equal, like I said, in my case here, I have this down here, minus 2, 9.81. So really what I'm doing, I'm summing the forces in the y direction. And so I'm going to have VE, and you could set this up in different ways. So we have VE equal to this, and then plus whatever you got for FBD here, times the sine of 75. So put whatever you have, and that will give you VE. Next thing we can do is we can say sum the moments once again, look at everything to the right of E, and let's sum the moments, let's say about E. Like I said, some people set up these internal loads a little bit differently. Once again, I'll do so if we want to sum the moments, so we're going to need this distance here. So the distance between that E and B is 0.035. So you have your FBD, which you found previously, then sine 75 times 0.035. So this is going to give you the vertical force for FBD, and then multiply by its moment arm, which is 0.035. Remember, we're something about this. And then you're going to have this, and that's going down, or that's in a clockwise direction. And that's going to give you -2, again, in my case, it was 2 kilograms, 9.81. Then times the moment arm from E out to that point there. And again, in my case, that distance is 0.35 plus 0.230, because this is on mine, this is 0.230, and then plus ME. So again, we have here is, this is the force here, and this is the moment arm. And that will give you, and if you set this all equal to 0, this will give you your ME. And finally, to find the N, sum everything in the X direction. So you could do like N, and the only other thing you have in the X direction to the right of E is just this force here. And so that's going to be N minus whatever you got for your FBD cosine of 75 degrees equals 0. And that will give you your N. Now let's do 715. Again, as always, you want to make a free body diagram. Now, notice we're only interested in what's happening at the internal loadings at D. So we only need to maybe make a free body diagram of that upper beam. And so over here at B, we're going to have like an X and Y component. Then over here, we have a D. Then at H. And 2 foot here. And then we have at H here, we have something coming down. Some force at FGH. And according to the picture here, that's going to be, our little triangle is going to be like 2 by 2, huh? And of course, that means then that these angles are all going to be 45 degrees. Then we have a load over here. Now mine, it's 150 pounds. So again, if we're looking at D, all we need to do is look to what's happening to the right of D. So let's take a look at that. well, excuse me, we have to do one thing first. We're going to have to find FGH first. So we're going to still have to work with a whole free body diagram here. So let's sum the moments about B, set it equal to 0. And again, so like here, look at all the moments. This is going to be 150 times 1, 2, 3, 4 feet, huh? So 4 feet. And again, it's minus because it's going to turn this clockwise about B. Then we're going to have this load right here. And we want the vertical component. And so that's going to be plus FGH times sine of 45 degrees. And then the moment arm to that is going to be 2 feet. Again, just the stuff that you've done before. So, that's going to be this component right here is going to cause the moment about B. And that's going to be 2 feet away from B. And it's going to be FGH times the sine of that. Set that all equal to 0. And that will give you your FGH. So then just look at your element. So we want the stuff that's happening at D. We have things like that. So once again, you can sum, say, the forces in the y direction, set them equal to 0. Like I say, for these internal ones, you may do this a little bit differently. Sometimes they do it this way, sometimes the other way. So we're going to have our VD. And then over here, let's see what other forces. Remember, we're only interested in stuff to the right of D. So this one is going to be negative 150. And then we're going to have the FGH in this direction here. And again, that's going to be the cosine. Excuse me, it'll be the sine again, won't it? So it's going to be plus FGH sine 45 degrees. And set that equal to 0. And just check your signs and everything, see if everything looks correct. It looks like if we end up getting a negative on this, it means we put this in the wrong direction. And so that'll give us our VD. Then same deal, sum the moments about D, set it equal to 0. And once again, we're looking at the moment from D of this force here. So that's going to be your FGH sine 45 times 1 foot, because it's only 1 foot from D. And then minus the 150 times 3 feet. And then whatever your MD is, and set that equal to 0. Just check the signs. You may have a different way of doing this with these internal loads. So just check that. Then finally, sum the force in the x direction. And that's going to be, let's say if we have n going this way, it's going to be n. Now this is showing it going this way, so that's going to be n minus FGH cos 45. And and set that equal to 0. So you can find V sub D here, MD here, and N from here. Again, remember, first you had to find the FGH. And plug the FGH down into these. Okay, this one's a little bit harder to visualize, but it looks like what they're trying to say, there's some kind of a bolt in here that has a diameter of 6 millimeters or 0.006 meters. And then this thing, there's a, excuse me, this is going to go down. There's a couple applied here. But it's actually sort of attached to this out here, which has a diameter of 0.012. So I think what we have, so the idea is, if we maybe once again make a little free body diagram here, that's up, and that's 20 Newton, 20 Newtons. And so this thing is going to be like maybe applying some resistance. Call this F here, and F here. And this radius on this is a little bit confusing because the radius on one is the diameter on the other. So this radius looks like it's 0.06. So what we're going to have, if we say whatever that center is called, they call that center B. So let's sum the moments about B. And so we're going to have, you could treat it as a couple. I'm going to just treat it as a moment. So over here you have 20 times 0.25 plus 20 times 0.25. And then over here, you're going to have in the opposite direction, F times 0.006 minus F006. Set that all equal to 0. Now using the, again, I'm using the values I had, which were 20 newtons. When you do this, it's going to give you a force of 833.33 newtons. And then that's going to cause a shear. And so we're going to need the area of that bolt, which is going to be 0.25 pi 0.006 squared. And it is saying it wants the average shear stress, and the average shear stress is simply going to be tau equals a force divided by the area. Again, in my problem, I worked that out to be 833 newtons, 0.25 pi 0.006 squared. And work that out, and that will give you the answer. So for this next one, best thing to do is like, so you're given a force P and use whatever value they gave you. And now let's start at joint C and do, just as you were using the method of joints for this joint. And so again, sum the forces in the X direction, set that equal to 0. And notice that our triangle, based on the dimension we're given, this is going to be like a 3, 4, 5 little triangle. So you can use that or use the area. And so this is going to give you like P minus FCB times 4/5 equals 0. And you can find FCB from that. And then in the same way, sum the force in the y direction. That will give your FCA. So do that first of all, find those values. And then go to joint B. So go to joint B. And so at joint B, of course, you can use the FCB you found up here and do it down here just in the opposite direction. And then sum the forces in the x direction, set those equal to 0. And from this, you can find FAB. Just sum these. And again, remember this little triangle is going to be 4, 3, 5. And that'll give you FAB. Then, so once you found those, you can then just go and use your, find your stresses. So it's going to be the stress in CB is going to be whatever you found for CB divided by the area of CB. And I think the area on all these were the same. It's, again, on mine, they were all the same diameter. And then do the same thing for AC. By the area. Like I say, just use whatever you found for AC, calculate this. And finally, AB. And calculate that. Now for 7-37, what we're going to have to do first of all is we're going to have to find FAB or BA, whatever you want to call this one, because this was A and this was C. So we're going to have to find FBA in terms of F. And then we're going to have to find FBC in terms of F. So what we're going to have to do is sum the forces in the x direction. And that's going to give us FAB cos 30 plus FBC cos 45. Set that equal to 0. Then if we sum the forces in the y direction, it'll be FAB sine 30 plus FBC sine 45 minus F, set that equal to 0. Then, because here we have two equations and two unknowns, so what you'll have to do, you can either do it by substitution or do them simultaneously. Solve for FAB in terms of F. So what you'll have some number, you have some number here times F. And then same for FBC, you'll have some number here times F. And then what you'll do, you'll put it into your stress equation. So let's say you end up having like whatever your allowable stress is. And let me just take a look at that problem. And like say, yeah, whatever your allowable stress is, and put that into here and set this equal to your FAB divided by your area, the area of that particular table. So that'd be the area of AB. And then same thing over here. Put your FBC divided by the area of BC. Just be sure that all of your units are correct. In other words, if you're putting this in terms of meters, be sure you change everything to meters. So again, you're going to put this into here, this into here, and then solve for F in each of these. So you're going to get solve for F and pick the lowest F. So you'll get an F when you solve this one. You'll get an F when you solve this one, then pick the smallest one. Now, when you put your allowable in, like on mine, I think the allowable was like 150, what did it say? 150 megapascals. Remember to change that to Newton meters squared. Remember, you have to add like 10 to the 6 Newton meters squared, like say for your allowable, same thing over here. That's going to be your allowable over here. So once again, find your FAB and FBC in terms of this unknown F. You have some number times F. Put that into the equation for stress. Be sure to divide it by the area of AB, and you'll get a value of F here. Same thing here. Put your FBC here, divide by the area of BC, give you an F here. So you have two values of F, and pick the smallest. Again on, excuse me, it's 759. We're looking at 759 now. Again, want to look at the free body diagram. But remember, so you have this uniform load. And so the first thing you're going to need to do is find out what the load is. And since it has both a triangular piece and a rectangular piece, you're going to have to separate these. And so this is going to be F. So the force here, I don't know if you want to call it the resultant force or the force of this triangle is going to be, remember, 1/2 the base, which now in my case, it was 18 feet across, times the height. Whatever that difference was, remember, wherever this triangular part started. So that's going to be, I don't know, let me call that just H1 here, maybe. Would be like whatever this was here. Then now for this one, maybe R2 is going to be, let me show it like this. So your R2 is going to be, once again, it's 18 across times whatever this height was. And now remember that the resultant is going to be, for the triangle, it's going to be 2/3 across. So that's going to be 2/3 of 18. So that's going to be on, at least on mine, which is going to be 12 feet from this point over here. This end here was A. And then, of course, this for a rectangle, it's always going to be in the center. So this is going to be like 9 feet. So then if we look at the free body diagram, it'll be FA, FB. Again, this free body diagram of the, what is it that we have there? It's like a beam. Free body diagram of the beam. And so you found like a value R2 here. Like I said, this would have been R2 times H2. R2, please put that in when we found this result to be 18 times H2. And for the triangle is 18 times whatever that H1 was. And so we have this. Then we have this one here. And we said this was out at 12 feet. This was out at 9 feet. So what you want to do then is find FB and FA. You can sum the moments. So working with this down here, sum the moments about A, set it equal to 0. This will give you FB, and sum the moments about B. That will give you FA. So you've got those. And then so for each side here, then we know that there's going to be a certain load. So let's see, there are 4 nails. So we can assume, so whatever your FB is, you can say, so for 4 nails per side, let's say four nails at A, that means the force per nail, this is at A, is going to be whatever FA is divided by 4. There's also 4 nails at B. And the force there is going to be FB divided by 4. And then so for each of these, look at A and look at B, and then put these into your equation. So use your shear equals, say, your FA divided by your area of nail. And then this is going, and then you're given this allowable. So you'll be able to solve for area. And then for diameter. And same thing for FB. So area of nail. And then you can solve for area and the diameter.